Hello everyone and a warm welcome to the lab number 17 titled Determining the Laser Wavelength Using Grating. In this lab we are going to observe and explore yet another important phenomenon that's associated to the light, namely diffraction of light. In addition to the reflection and the refraction, diffraction is the phenomenon that can only be explained if you're looking at a light as a wave. Diffraction of light is a phenomenon that happens when a light passes around a corner or through an opening or a slit whose size is in an order of scale of the wavelength of light. And when that happens, there's multiple waves that are being produced that interfere with each other, producing different types of effects that we commonly define as interference of light or diffraction of light. So in this lab, we are going to explore this important phenomenon that has found many applications in real science. As learning outcomes for this lab, we are going to define what a diffraction of light is, what are the specifics of a white and monochromatic diffraction of light, and finally, as a hands-on part of this lab, we are going to set up an experiment in which we are going to observe the phenomenon of diffraction through the diffraction grating and use it to measure the wavelength of our red laser diode module. The equipment that we are going to use in this lab consists of red laser diode module, laser holder made out of wood, a diffraction grating, a lens holder that we are going to use to hold the diffraction grating. We are going to use the measuring tape, and finally we need a pencil and large white sheet of paper. Here I established the setup for this lab. As you can see here in the back, I have positioned the red laser on a laser holder, taped it down, and also I positioned here the measuring tape. Zero position, and the measuring tape is exactly at the aperture of the laser. And then here in the back, I have the back screen, and in front of the back screen I have a diffraction grating that's being mounted onto the lens holder. So at this point, the red laser is shooting the laser beam, and you can see that this laser beam is hitting the diffraction grating at this point here. And then the diffraction takes place at the diffraction grating, and as a result of the diffraction of the laser beam, you see three distinct red spots on the back screen. Now what you can also observe is if you are moving the diffraction grating closer to the laser, the distance between the red spots on the back screen is changing. The spots are kind of getting farther away from each other. And also if you're moving the diffraction grating further away from the laser, you can see that the red spots are getting closer, and not only that they are getting closer, you can also observe the appearance of the two extra spots, red spots here on the left hand side and here on the right hand side. So all these red spots that you're seeing on the back of the screen are a result of the phenomenon of diffraction that's taking place on a diffraction grating. Now what you want to do is you would want to make them reasonably far, and you also would want to position this diffraction grating so that the appearance of the red spot is symmetric, meaning the distance from the red spot on the right hand side to the center spot is approximately equal to the distance from the left hand spot to the center spot. Once you establish the symmetry, meaning the distance from the left hand spot to the center spot is the same as the distance from the right hand spot to the center spot, you would want to mark the position of the diffraction grating, and then also you would want to mark the red dots that you're seeing on the screen. So we are observing the diffraction grating at a position of 42 centimeters, while the back screen is at a position of 62 centimeters. So the distance from the back screen to the diffraction grating is equal to 62 minus 42 centimeters, or 20 centimeters. So let's remember this number, distance from the back screen to the diffraction grating being equal to 20 centimeters. Okay, so here's our sketch. As you can see here, we have three marked dots that correspond to the three red dots produced by the laser on our screen. So the first step, we are going to create a line through the centers of these three marked dots. And then we are going to measure the distance between the left dot and the center dot, and then between the center dot and the left dot. So I'm going to label the left dot with the letter L. Center is going to be labeled as C, and then the right dot is going to be labeled as R. So the distance between the left and the center dot is to be labeled as x1. And then also the distance between the center dot and the right dot is going to be labeled as x2. Okay, let's now measure the x1 and x2. So it looks like the x1 is about 7.1 centimeter. So our x1 is equal to 7.1 centimeter. Let's measure x2. And as you can see, the x2 is about 7.2 centimeter. Now we can find the average between these two distances. So our x is going to be equal to x1 plus x2 over 2. So if we substitute 7.1 centimeter for x1 and 7.2 centimeter for x2, we're going to find the average of 7.15 centimeters. Now, if you remember, during the lab, we also measured the distance between the back screen and the diffraction grating. And if you recall, we measured the distance of 20 centimeters. So we're going to write for L, capital L, 20 centimeters. Now, the angle theta that two laser beams made when they produce the left center and right spot. So if you're measuring the two laser beams, one that's producing the left spot and one that was producing the center spot, that angle would have been labeled as theta, and it can be calculated as inverse function tan of x over L. So in our case, we have inverse tan of x being 7.15 centimeter over capital L being 20 centimeters. Which gives us inverse tan of, these units can cancel. And here's 7.15 over 20 equal to 0.3575. And if we calculate the inverse tan of 0.3575, so here's the inverse tan, gives me 19.67. So we are going to round it to 19.7 degrees. So this is equal to 19.7 degrees. You would want to look at your diffraction grating, and if you look at this diffraction grating, you'll see that the diffraction grating that we used has a total of 500 lines per millimeter. So what really this 500 lines per millimeter means is this diffraction grating is made out of a whole bunch of slits, and those slits or those lines, turns out that there is a total of 500 of them within a length of 1 millimeter. So what we want to calculate here approximately is what is the distance between the two neighboring lines or two neighboring slits. So if we have a total of 500 lines in a millimeter, it just takes a following calculation. So you would want to take a total length of 1 millimeter and divide it by 500 to come up with the distance between the two slits or two lines in your diffraction grating. So my D, or distance between the two neighboring lines, is going to be equal to 1 millimeter over a total of 500 lines. And if I do this math, so if I take 1 over 500, I get 0.002 millimeters or I can convert this to 2 micrometers, or even better, 2000 of nanometers. The reason why I'm converting all this into nanometers because ultimately we're going to be calculating the wavelength of our laser beam, and that wavelength is going to be given in nanometers. So at this point it's the best to convert everything into nanometers. Okay, so that's my distance between the two lines in a diffraction grating. Keep in mind that your diffraction grating may be different. You may be having 1000 lines per millimeter or some other diffraction grating, so you would want to make sure to take that into account when do the calculation where you will be figuring out the distance between the two neighboring lines in your diffraction grating. Now that we have a D, we can calculate the lambda of laser light. Lambda is going to be equal to the D times sine of the angle theta. So in our case, D is equal to 2000 nanometers multiplied by sine of our 19.7 degrees. How much is the sine of 19.7? So here's 19.7. Sine is about 0.337, and then multiplied by 2000 gives us the wavelength of 674.19 nanometers. So we can conclude here is that the wavelength of the light that our red laser diode module produced is about 674.19 nanometers. As you can see, this is in a red spectrum, which is kind of expected because our laser diode module produced the red laser light. Okay, now it turns out that the nominal wavelength of our red laser diode module, lambda nominal, is equal to 650 nanometers. And now that we know the nominal value for the wavelength of our red laser diode module as well as the measured one, we can calculate the error of our measurements. So the error percentage is going to be equal to lambda calculated minus lambda nominal absolute value over lambda nominal times 100. So we can substitute for the values here. So for the lambda calculated, we have 674.19 nanometer minus nominal value of 650 over 650 times 100. So this ends up being 24.19 nanometer over 650 nanometer times 100. So here we can use the calculator. So we have 24.19 over 650 times 100 gives us 3.72% error. So the error of our measurement is about 3.72%, which is pretty good for this type of measurement.